Don't be afraid to be like, demanding.
Yeah.
Yeah. I just want to check really quick before we get started. I believe Ellie's on the call.
Yeah.
Ellie, can you type in the chat to make sure you can hear us? Can you hear us fine? Yeah, I think so.
Yep.
Yep.
Okay.
Cool. Try to stay close to the monitor
I
if
will.
you can. And then here, I'm sorry. Yeah, I'll let you do it. Just yeah. All right.
All right. Hey, everyone. I'm Raphael. I'll be giving the lecture today. I'll be talking about plotting in Python. So yeah, it's week 4, second lecture. This is a cool picture of a sunspot and the ISS flying by. Thanks, Elon, for putting it up. So yes. So here are announcements. The third, I think Elon was saying he took that picture. So very impressive, Elon. Yeah. The third homework is due next Tuesday. So that'll be the 21st, I believe. Yeah. And office hours today, 3:30 to 4:30. Megan will be filling in for Emily. So come say hi to Megan. And thanks to those who showed up yesterday. We have office hours every day. So every day of the week. Yeah. And attendance, fill out the QR code. If that's not working for, oh shit, yeah. My bad.
I was like,
Yeah. Okay, yeah. So attendance, the link is here. If the QR code is not working for whatever reason, if people want to put that in really quickly.
Maybe you can move the thing so it's out of the way, the QR code. People can scan it.
Oh, wait. Yeah. All right, so it seems like everyone's ready. Yeah. Okay, so we're gonna go over what we did last time really quickly. So Elon talked about NumPy. So we'll go over a couple questions. You guys can talk for 5 minutes or so. So what is the difference between a NumPy array and a Python list? And why would you ever want to use a 2D array? And what do they remind you of? So you guys can just talk in groups at your tables for 5 minutes about this. And yeah, I'll ask for an answer in about 5 minutes. So go ahead. Yeah, I'm still right. And in the chat, if you guys want to type anything, that's good too.
Maybe like, can you see it? Okay, yeah. Just in case. How did you make it go away like that?
I don't know. Oh, it doesn't.
Oh, I think there was one.
Yeah. Yeah, I downloaded. Oh, yeah. There. Yeah. Yeah. What? I know. And I'm just gonna sit on the hill. I'm just gonna sit on the hill by this. Yeah. And not actually. But I definitely.
All right, I think it seems like everybody's talked. So anyone want to go ahead and tell me what the difference is between a NumPy array and a Python list? So someone say sure. Any? All right, you.
I guess like a list, you can store any data type, right? And have it in that list, and to call on to each item, you have to use the index.
Yeah.
You do that for iteration. But an array, the benefit is you can kind of act on the entire array at once with like math functions.
Yeah,
So it's like a matrix. So it's like beneficial in that respect.
Yeah, that's exactly it. And I guess that sort of answers the second question too about a matrix. But yeah, why would you ever want to use a 2D array? Essentially, because it can replicate a 2x2 matrix when a list couldn't do that. So yeah, that's a little more about NumPy, which will be useful today. So in NumPy, you can create arrays with a specific range or number of items using either numpy.arange, where you do a start, stop, and step. So essentially, if you wanted to go from 1 to 100 in increments of 2, you would go numpy.arange 1, 100, 2, and it would go 1, 3, 5, 7, etc. NumPy.linspace is similar, so but except the last argument is number of steps rather than the step size. So you would want to do numpy.linspace from 0 to 2 pi and make 100 steps. You do numpy.linspace 0, 2 pi, 100 steps, and then it would do 2 pi over 100 would be each step size. And these are very important for plotting and very similar to just the basic range function that's implemented in Python. So now we're going to talk a little bit about how to get data for plotting for scientists. This is James's meme. I won't take credit for it. So yeah, we'll talk about data. So the main way we get data is we'll load it from various formats. We can import it to our Jupyter notebook using numpy.loadText. So numpy.loadText is a NumPy argument where you call the file name in quotes, because it'll always be a string, I assume. The delimiter is none. The delimiter is where you specify the way that the data is partitioned. So essentially, in this case, it's fine because it's just a bunch of values. But if you had comma separated values, you would put delimiter as a comma. Skip rows means however many rows you want to skip at the beginning before you start getting the data, because sometimes there's some text at the beginning of data files. Use columns is just whether or not you want to use the columns, and unpack equals false is if you wanted to assign variables to the columns in the data, you would say unpack equals true and assign that as X, Y, Z, etc. Or you could use that to sort of get the transform of the data. So if it was say a 10 by 15 data set, you could make it 15 by 10 if you wanted to do that for whatever reason. And yeah, that's how you sort of load data with NumPy. So you can, so here's an example. Data equals np.loadText, some sample data equal .txt, skip rows equals 1, because the first column, or sorry, the first row will often be the text that describes the data, and you can sort of keep that in your head. And also, if you do this and there are string values that are confusing to NumPy, it'll give you an error. So it's often better to just have the numbers, and then you can print the data and see the data. So if you're looking for the specific values of the data, you can use extremely useful function numpy.where. So we can use NumPy to find indices of specific data. So essentially you do numpy.where some condition equals true. So as you can see in this example, we say A is numpy.arange of 10. So it'll go 0 to 10, sorry. And if you call numpy.where A is less than 5, it'll give you all the values in which A is less than 5. So 0, 1, 2, 3, 4. You could do greater than 5, it'll give you 5, 6, 7, 8, 9. And yeah, that's the way NumPy. You can use it for also far more complicated arguments. If you wanted to get the index of the max of the data, you could do numpy.where A is equal to np.max of A, and then it would give you 9, for example, or something like that. Or you could even call the argument by doing .argmax at the end. It will give you the actual index value. So that's the case where the data is not incremented like this. If it's not going from 0 up to 9, if you had data randomly, if you had like 3, 5, 7, 8, and you didn't know where the max was, you could use numpy.where to get that, for example. And here's, yeah, another example where you call numpy.where the same condition, but now you want to multiply those values by the other values by 10 essentially. So that's the last argument, what it's doing. So essentially what it's doing is it's getting the values that are less than 5, calling them on A, and then multiplying the other values in the array by 10, which is the last argument. So you see 50, 60, 70, 80, 90. So now we're going to talk about how do we represent data after getting them. So these are a bunch of cool plots, a variety of plots, I think, some contour plots and some HR diagrams and stuff like isochrones, if I remember 160.
For the videos, can you make it so that's only one box?
Yeah. Oh, yeah. Yeah, there you go. Yeah, so yeah, these are isochrones, if I remember 160 correctly. But and this is a water vapor plot. These are just cool plots that have all been made in Python, and we will show you how to do all of this. So yeah, plotting is extremely important, obviously, to all scientists, and it's probably the main use of Python for scientists because you can plot your data in a variety of ways, and there are a variety of packages that we will teach you about, like pandas and stuff that can be used to plot things that are extremely useful and efficient. So now we'll talk about what packages to import for basic plotting. So you just import matplotlib.pyplot from that library, import it as PLT. And whatever, yeah, exactly. Whatever type of research you do, you'll need this. No matter what, essentially, this is how you always plot things in Python, whatever you're doing. So we'll begin with the simplest case. So if you import that package first, you can essentially plt.plot an array, and plt.plot calls a variety of arguments, which we'll talk about, but the most important are the first two, which are x and y. You can even plot in 3D, but we'll talk about that later. But for now, we'll just talk about the first two arguments would be x and y. So if you set x to be some type of range from 0 to 3 and y to be 2 times x, you could plot x and y. And as you see, this is exactly what it would create. Y equals 2x plot from 0 to 2 because np.arange3, as Python always does, cuts the last digit, which would be 3. And also importantly, after you call these things, you need to write plt.show, because then it'll actually show the plot, essentially sort of creating a canvas for you to work with. Yeah, go ahead.
So is like X array, we already made those already?
Yeah, exactly. They always have to be defined beforehand. Otherwise, it'll give you an error. Exactly.
Can they be different sizes?
No, they always have to be the same size. There are ways to do it if they're different sizes, but we'll talk about that later. For now, just make sure to keep them the same size. Otherwise, it'll get confused. Yeah, so that's the basic array. So now we can talk about plotting a curve. So if we have the same x a range and y equals x squared, these are all just functions we'll show you how to plot. So if we plot plt.plot x comma y, you can see that we get a plot like this. So that's essentially the plot of x squared, which, yeah, from 0 to 2. And as you can see, it's a little weird because it just took the values at 0, 1, and 2 and connected them. So if we wanted to do it better, we would maybe do np.range from 0 to 3 and 100 points. So then you would see the actual parabola, because obviously this is not what an x squared plot would really look like if you went from 0 to 2. But what plot essentially does is it connects all the points it has. So right now, right, it has 0, 1, 2, and then the corresponding y values of 0, 1, and 4. So it's just making lines between those points, essentially. So yeah, that's, yeah. So exactly, so this is how we would correct that. So you go np.linspace 0, 3 and 100 steps, and you do y equals x squared, and now you get the parabola that you would expect for an x squared plot. So you could even plot multiple curves. So if you did x as a linspace from 0 to 2 pi in 100 increments, and you can plot np.sine and np.cosine. This is why NumPy is also useful, because you can call these math functions, as we were saying before. And if you show them, you can see both plots, the cosine starting at 1, the sine starting at 0, going throughout. But yeah, this is why these np.linspace arguments, or defining x variables and such as np.linspace is important, because otherwise it'll try to connect a very limited amount of points and the plot will look very wonky. Yeah, go ahead.
Could you show the np.linspace of the last one?
Oh yeah. So
Wait, so could you explain that?
Yeah. So np.linspace, it'll go from 0 to 3 in 100 steps. So it'll go from 0, I guess, it would go to 0.033, 0.066, 0.099, and then on and on and on up until it gets to 3. And yeah, that's why it looks much more like a smooth plot. So yeah, this is how you do the sine and the cosine plots. And yeah. So yeah, essentially it's really useful because you can plot multiple curves on the same plot, say 4 curves. If you wanted to plot x to the 1, 2, 3, 4. So as you can see here, we're making plots of y equals x, y equals x, y equals x squared, y equals x cubed, and y equals x to the 4th using a for loop. So we're looping through 1, 2, 3, 4, plot x comma x to the 1, and then as you can see here, x to the 4th is the plot going up in light blue, I guess. X cubed is in purple, x squared is in blue, and x is in orange. And yeah, you use plt.show to show these plots. So now plt.plot will connect the points, but if you have, for example, if you're doing research and you have a bunch of scattered points, like say you had values that are sort of not necessarily, you don't even know if they're correlated, so it's unclear what the function would be, you could just plot a scatter plot. So that the argument for that is plt.scatter. So essentially what this is doing here is this creating np.random.ran creates 20 random points in x and 20 random points in y. Sometimes this is the type of data you would be working with where there is no correlation at all and you just want to see what the plot is looking like. So then you would scatter x and y and show it, and it would look something like that with the orange points all over the place. And I think random goes from 0 to 1, and so then you have 20 points between 0 and 1 on both x and y, and that's what it's plotting right here. And as you can see, it just creates dots. And yeah, as I said, this is often the easier way to look at data because sometimes you're not clear what the function is. And if you were to try to plot it, it would look extremely confusing and there would be lines all over the place because Python would try to connect all the points with plt.plot. So you can also use different type of plots in one plot itself. So every time you hit plt.show, it's essentially a new canvas. So everything before the plt.show will go on the same plot. So for example, as we can see in the commands here, you have xx equals a linspace from 0 to 2 pi, y equals sine of x, and then you can plot and scatter. So as you can see, it looks roughly the same, although there's an offset. As we put on y, we put the offset of 0.5. So they're the same plot, but we've put 20 points because it's easier to see the different points. If there were 200, it would look very similar because the points would be very close together. And yeah, as you can see, everything up to plt.show will be shown on the graph itself. If you wanted to make 2 separate plots, you would go after plt.show and write a new plot again. So yeah, you can put all types of arguments to plotting. You can scatter x, y with the color. You can specify the size. You can specify the opacity of the scatter points, which is essentially like how bright they are, if you want them fully bright or sort of transparent. And you can specify the marker style. So a star would mean it would literally plot a star as the scatter point rather than just a regular circle. And importantly, you want to label things always. So you can do plt.x label and plt.y label will label the x and y axes, and plt.title will allow you to title your plots. So yeah, to make different axes, they're more advanced and more flexible, and we have colorblind plots. But yeah, I really think that probably the easiest way to learn this is through doing. So I have a demo for everyone that I'll pull up here. I put it on B courses. So if you guys could open it, that'd be great. So we'll be looking at the plot of a type 2 supernova, the light curve that I've been working with recently, and I'll try to show you all how to plot it.
So I didn't get a chance to write down.
Yeah.
So is there some way to access the slides?
Yeah, we'll post them. I can also go back a little bit. Sorry?
Just for doing the problem on.
Oh, yeah. I'll go back and forth. I can show you guys. Yeah. And I'll also type in what I'm doing. But yeah, so yeah.
Can you command plus a couple times so it's bigger for the
Yeah, okay. Okay, yeah. So yeah, I realized I went through that a little fast, but I think it's easier to see than to see it on a slide, to actually do. So yeah, so here's what we'll do. We'll start by importing numpy as np, and as I said, matplotlib.pyplot as plt. So yeah, you can do that. Hopefully this works. Yeah. So actually, wait. Let me just check before. Is everyone able to open this? They have this Jupyter notebook open right now?
If anybody needs help opening it, just raise your hand and we can come and help you out.
Yeah. And make sure you have that data file that was in that folder in the same directory, because otherwise you won't be able to see.
Wait, what do you mean the same direction?
Like when you put this, you have like a home directory where you work from, right? And you put it. Did you put the other file in there? Like if you download it and move it into the downloads thing. Oh wait, now it should be fine. Did you open this from downloads?
Yeah.
Or if you want, we can go around so you can give a lecture.
Yeah, I'm just trying to make sure everyone has it.
What about, can we just upload the data to the Jupyter notebook?
Yeah, well, that's what we're doing here, but the issue is it needs to like be in the same place on your computer.
Yeah. Well,
So yeah, if it's all in downloads, then that's fine.
I look at my
Yeah, sorry.
No, just like.
Oh, you can get
Okay, I had the same thing, and I just went back.
I'm sure.
I'll open the file into like the Jupyter notebook. You know what I mean? Like if you go to like the home of Jupyter.
Does anybody else need help getting it open?
And then you upload the data, then now my phone's better. Oh, okay, so.
Okay, so yeah, so essentially what you want to do is if you have everything in downloads, this should hopefully work. So if you run this cell, it'll load in the data as I said. So like we said, we don't want to mess around with the transform or anything. So I'll run unpack equals false. And then we can take a look at the data by just looking at it right here. So the data is a bunch of arrays and a bunch of, rows and columns. So the rows, essentially the way it works is I've removed the first row that explains it because it makes it easier to just work with it. But the rows go, the first one is the date, the entry in the data file. The second one is the date. The third one is the star they're looking at. It's always the same star for this. And the fourth one is the B magnitude. The sixth is the V magnitude. The eighth is the R magnitude. And the 10th is the I magnitude. All other values are errors on the magnitudes. So I realize these words may be a little confusing. So when I talk about magnitudes, that's essentially the brightness of the star at various points or the supernova. So this data describes a star that has exploded in a violent explosion after going over its Chandrasekhar mass in its core, which means it started fusing iron and become extremely bright. In fact, as bright as the host galaxy it's in. So it'll become extremely bright, and we are highly interested in these objects as they can work for distance ladders, or actually not type 2s, but they can work to understand stellar physics in a variety of ways. And yeah, so the magnitudes just describe how bright it is over the course of time, and the errors are as you would expect. We get errors on the magnitudes. So if we go down here, we can get the data. So we haven't completely shown you guys this yet, but if we want to make empty arrays, the way we would do that is do numpy.empty 0. So that would create an empty array with nothing in it, because that's what we want. So we want to append to these arrays like we talked about last time, like Elon talked about. So the way we would do that is, for example, for date, we would run numpy.append date and then data. We need to run actually a for loop, right? Because we have like 30 rows and we want the value of the date in every single row. So we'll run for I in range len data. We'll say date is equal to numpy.append date data I 1, because as you know, the second value will actually be 1 because Python index is starting at 0. But essentially what this is doing is this is just adding every single row from 1 to 30 and the first column. So the columns are the data and you want to add from every single row, and that's why we loop through it, because otherwise we would only get one of the values. And you can do the same thing to get the other values. So you would go data I 3 and you go, these are the values in which the magnitudes are stored. Oh yeah. BVRI, sorry, are different filters. So different filters are different wavelengths in the telescope, and essentially you're measuring the light at each of those wavelengths, and you're getting the brightness at each of those wavelengths. So BVRI are various values. So I is infrared, so it's high wavelength, roughly 800 nanometers, which is on the non-visible range of the spectrum. V and R are both visible, but R is a little more reddened, and B is the closest to ultraviolet light, but it's not quite. There's a U filter, but that's not in this data set. So yeah, so this is how you get all the data. Oh yeah, my bad. Thank you. Yeah, so now what we would do is we can take a look at date. Oh yeah, and the date looks like this because the date is in modified Julian days, which is a way for astrophysicists to measure the days since the Julian calendar was invented in 52 BCE by Julian in Rome. And these days are actually, but this is a more modified Julian date. This is the date since November 17th, 1858. I do not know why that day is so special, but that's what these numbers are. So that means this data was taken like 2016. So that's 57,000 days later, essentially. And this is just the way astronomers count dates. It's a little confusing, but yeah. So then you can see B, and you can see the magnitudes. So nan means not a number. It means there was nothing recorded that day for the data. And you can see the different magnitudes. Magnitudes are generally for supernovas at their brightest in the range of 14 to 17. They're usually brightest in the infrared, if I'm not incorrect. Yeah, they'll be closest to 14/15, whereas in B, VR, they'll range up to 16 and 17 at their brightest points. And then later in their lives, they can go all the way to 22, 23 magnitudes. So yeah, I realize I'm going up in numbers and saying that's less bright. So yeah, magnitudes work in the sense that the higher a magnitude is, the less bright it is. So an object at 10 magnitude is extremely bright, whereas at 20, it is not nearly as bright. So yeah, now we want to try to plot the data. So in order to plot the data, first we got to create our canvas. Yeah, sorry. Oh, my bad, thanks. Yeah, R and I should be different values. Yeah, the I should be the 9th column. But now we can plot. So in order to plot, the first thing we do, which I didn't really mention in the lecture, but we want to use plt.figure, because this way we can create our canvas with specific proportions that we like. So 12,8 is just a tuple that specifies how big you want it. I'm not sure if it's actually in inches, but it's a way to make it bigger and smaller by changing those numbers essentially. So what the first thing we want to do, just to see at first, we could plot plt.plot date comma b, and as you can see, it's not great because it's trying to connect all these points together. It's confused, and yeah. So the first thing we would actually want to do is, because magnitudes work in the reverse direction, we want to make it upside down so that it looks more normal. So the way a supernova light curve should work is it should rise initially and then flatten as it goes out because of the cobalt decay. So initially they get extremely bright following them reaching their Chandrasekhar mass. And then as cobalt begins to ignite in the star, just it radioactively decays. And that's why you see this long decay. And some supernova are even visible 10 years after they've gone off. So that's roughly what we're seeing here, but we can obviously make this much better. So for example, we can put in a marker, which will specify to Python that we want it like this instead of trying to connect all the points. So the marker, this caret signifies that we want triangle marker points. And we can make it have a color. So for B, we'll say blue. And we'll say label. So this is another argument. Plot takes tons of arguments, but just to show you, just matplotlib color. You can look, there's tons of colors over here that any of which you can choose from. These are the base colors, and there are all these other colors. And we can make it like this. So here we see the B light curve, and then now if we want, we can plot the V light curve, and let's say we want a caret that's D, which means like a diamond, essentially. It is a diamond. And for V, we'll make it green. So we'll have it like that. And as you can see, the different magnitudes at different wavelengths, the supernova will obey different light curves or get to different magnitudes. And we can do the same thing for R. We can make it like so, and then we can make this will make it I believe a backwards triangle. Yeah.
Can you specify where the triangle label should be?
No, sorry, I'll explain that in a second. So in order to see the label, all you have to do is run plt.legend. And then the labels will go in the top corner. There is a way to specify where they should go, but I think for now, for this type of plot, it is fine to have them in the top corner.
Really quick, I'll just add in. All of it, like, we're not giving you like all of the little tiny tips and tricks you can do, but you can always Google like
Yeah.
move legend somewhere, and you'll find tons of documentation on all the little details. So if you want to tweak your plots to look like perfect. Right now, it's just putting the legend wherever it thinks it is best, aka where there's no data. But you can definitely change that, just like everything else in Matplotlib. It's very customizable.
Yeah. So for the last plot, we'll make it S meant square, by the way. V means inverted triangle, and we'll make it color. So now we'll do the color to be what Python calls exactly a hexagonal color. So these are essentially just numbers that you memorize that will give you a color that you want, essentially. So you'll see in a sec. So this makes this sort of not really sort of indigo color, which is what we want, but yeah, it's close enough. As you can see, this is why matplotlib is useful also, because there's not sort of an equal number of points. And that's why those NaN values are also important, because that tells Python that at those values, just don't plot, but don't give an error either, because it's not the same shape. So clearly, for example, there are more B and V data points than there are I, but it's fine because it just doesn't plot where there's an NaN value.
Did you make the figure size a bit smaller?
Yeah, yeah. There we go. Yeah, I'll make it a little smaller for now. Yeah. So as you can see there, we have our plot, and that's the light curve of SN 2016 GKG, which is a type 2 supernova. Like I said, came from a massive star of mass greater than 8 solar masses and less than 40. The supernova and the progenitor were discovered here at Berkeley. And if we want to make a title, we can just call it SN 2016 GKG. And it'll put the title right there. For title, you could specify font size or font style and stuff like that. You can put an X label, and we'll put modified Julian date and Y label magnitude. So here we have our plot, and if you just want to make it have a grid, you can do plt.grid. These are all just various arguments that you'll learn over time as you start to plot, but here we can see the rise and then the decay. And for the decay, we only have roughly 60 days since it started decaying in this data set. So this won't be perfect, but I also wanted to show you guys as sort of an extra step on how to overlay plots. Actually, before I do that, are there any questions about this? Oh, yeah, yeah.
Did you already filter out or remove the NaN values?
No, when you have NaN values, Python just says just don't plot there, but they're still in the data set.
Okay, because if I try to plot it, I get an error saying that X and Y must be the same first dimension.
Oh, wait, that's strange. So did you?
I just pulled it straight up. I assume you can just remove it by doing like X in the array for anything that's like true, and then
Yeah, you could do it like that. Yeah.
Was there anything specific that you have to do?
It should just work like this. If you append it like that, it should be fine. Like as we can see. Sorry, 1 second, I'll get to you. Because there are NaN values in B, V, R, I. Like as you can see at the end, like it should just say that there's nothing to plot there. I guess you could truncate it with numpy.remove, but yeah. You had a question there?
Yeah, I already saw it.
Oh, okay. Oh, yeah. Oh, back to the for loop, yeah.
Yeah, like this one is NaN.
So yeah, were there any other questions? The NaN thing, is anyone else having a problem with the NaN thing, or is it working? Yeah, the empty. Wait, you're getting empty, or are you asking? Oh, the empty. Oh yeah, sorry. I'll go up. Yeah, the empty just means to make an empty array of like with nothing in it. So we want to append to arrays. So just like if you make an, so just I'll just show you. So x equals empty to empty 0, and it'll just create an array with nothing in it. And then you want to append by adding the values from the data set into that array. So that's how you would do it, or that's the way I find the easiest. And I think you could, no, never mind. But yeah, that's how you would load in data and plot data. So if everyone is sort of on the same page with this, we can try the next part, but if also people have more questions, don't be afraid to ask. I'm trying to get you all to get this at least. The next part is slightly more complicated. Yeah. Yeah. The plot, yeah. Yeah, okay. So yeah, if everyone, I think, sort of has it hopefully figured out a little bit. Yeah. Oh, what? Oh, no, I made data with, it just depends how you defend it, define it, sorry. Like if you define data with a big D, you have to use the big D data, or if you define it with the little d. Yeah.
There's a reference, like, you look at the document. Yeah, all this.
Yeah, so just to clarify again, like plt.plot, you can just pass any arguments. The first two have to be x and y, but after that, these, like I said, the caret, the diamond, the square, the upside down triangle, those are called markers. You can specify color, you can specify label. And yeah.
Show them where they can find like various colors that they can put in, as well as like just how to like maybe go to the documentation page for PLC.
Yeah. Yeah, so yeah, exactly. Like you just said, matplotlib.org has an explanation of everything you can pass into this. So as it says, star arguments, which is any arguments. So this is plotting labeled data. And any parameters here, you can see all the parameters you can put in. Other parameters are all here. Every single parameter you could put in. Figure, label, pick. Yeah, there are a variety of parameters that you can use, which are super cool for looking at data. Let me see chat. Is there an established order to putting labels? Oh yeah. So no, there is no established order except that plt.show has to be last. Otherwise, it'll get confused on where things should go. To respond to that question. Yeah. Yeah, the upward arrow thingy is a marker, so that just means to make the points triangles. That's all it does. It's just the D is means diamond. It's just like different you can just look up plt.plot markers. Yeah. So you can look that up. There are a variety of markers you can use. So yes, S is square. And yeah. Yeah, sure. So yeah, real quick, just while people work on this, I'll just you can look at the challenge problem really quickly. So for the challenge problem, all we're doing is, like I drew up here, a bad drawing of a supernova light curve. But the point is that after a certain point, it should roughly decay in a straight line, like cobalt does. So we want to graph that. So it's just a straight line. And the slope, the way in which it decays, is it decays at a rate of 1 magnitude per 100 days. So every 100 days, it gets less bright by 1 magnitude, so it'll keep going up. So what you would want to do is, first of all, copy all this because we want to put it on the same plot. And then create a linspace from, I don't know, linspace from np.min of x to np.max of x, of date, sorry. And then what you would want to do is say y is equal to -0, or sorry, yes, -0.01 x plus b. And with b, you would want to mess around with it a little bit. As I said at the top, you're going to have to make it so that it appears on the plot. But one other thing is, because y is in these weird format where it's 57,000 days, you're going to want to subtract 576,760, for example, which will be the first date. And wait a second, I forgot to plot plt.plot of x comma y. So as you can see, yeah, as you can see, this is the way the line should appear roughly. because we only have the early time, it'll only appear like kind of like the actual decay. So essentially what we're looking at is that this line should resemble the decay going down here. In the beginning, it won't, but as we get towards later days, it would. So that's all we're looking at. And we could make, for example, so that it's more clear, we could specify an argument called line style and make it dashed. Wait, sorry. No, my bad. I put that in the wrong place. And here we go. We can see a dashed line, and we could label it cobalt decay. So as you can see, then it says that the dashed line is the cobalt decay, essentially. So we can see the similarities. I mean, yeah, clearly it's not a perfect fit right now, but later on it will get better as the graph sort of gets flatter. Initially, it's a very steep decay, but as the cobalt starts to emit light, later on, it'll resemble that line if we had later time data points. So yeah, go ahead. Yeah. Oh, wait, no, but if you update it in a loop, it'll create arrays like that, or it should. Like you see, because you have empty arrays and you're appending them with values from the data. And you should create equal size arrays, which you can plot against each other. The decay is going up because a higher magnitude is less bright. So the decay is going up in magnitude because as time goes on, it'll get less bright, but the cobalt decay is more measured than the actual decay of the supernova. So yeah, for this one, yeah.
Oh, yeah. Cool.
Yeah.
The third argument of like flat left to the top one you could have, you don't have line style equals the style.
Yeah.
You have to have line style. Oh, like in what context do you use?
I think you do line style when you want to make it clear to yourself what you're doing, really. And yeah, otherwise it'll understand generally what you're talking about because it only has certain arguments that sometimes the arguments sort of overlap that you can pass to marker and color, for example, but otherwise it'll recognize it. Yeah. Besides actually for label, I think you should always do that because otherwise it's highly confusing what it's talking about. Yeah. So yeah, it's 3 o'clock. I realize this was slightly complicated, but I wanted to show you guys a real way to use data in astrophysics and make a light curve for a supernova. And if you have any questions, let me know, obviously over email. I'll post the solutions to the B courses. And yeah, thanks very much. Ask me any questions. You guys can stay around if you want any help. Thanks.
Yeah, so homework 3 is going to be due Tuesday before next lecture. So make sure you get that done. I believe you will start using a little bit more of the NumPy and plotting. And from now on, we're getting into like real stuff that you don't learn in 61A and like real astrophysics / physics / any science useful tools. So please come. See you next week, and we'll talk more about plotting.
It's a library. It allows you to do all the
Great. Oh, really? This is amazing. Yeah. Great job.
Thanks.
Let's just stop sharing. And
No, I'm just saying it's tough to show because I realize it is a